All right. So what I want to do today is finish off a discussion on the second order system. So let's go to the economic engineering. Look at all the stuff it's done. It's hardly believable. So this was economic engineering. So now we're using the laws that we posited. So Newton's law, which is the law of demand, the dynamic law of demand, plus some force laws that we developed for economic forces naturally, which is our storage law and our friction law. So that gives us three elements. Very familiar elements. An I element, a C element, and an R element, if you know bond graphs. Mass, spring, damper, okay? An inductor, a capacitor, and a resistor, if you're electrical, or demand, storage, and intermediaries, market friction, right? If you're economic, all right? And these are enough to build interesting systems, especially if we put an exogenous force on it, there's an input on it, and we can get linear, we can build linear systems, passive linear systems, all right? So the first thing we did was look at first order systems. So they're called first order because they follow a first order differential equation, all right? So this was a demander, and he has his price. Every demander has a price. He has a quantity demanded, that's his velocity. And there's some, he has some desire, all right, so some want for stuff acting on it. And here is another demander or supplier, depends on the relative motion. This is a very inelastic market, all right, so it's not going to do anything. And they're connected through this intermediary, which is a damper, all right. And our result is this differential equation. So you see that what's happening is this intermediary is taking a price cut. So this is the damping rate, which is the discount rate. So it's measured in 1/time, and it takes a percentage per unit of time of the price. Okay, and that's the net force that has to be supplied by the external desires. All right, so completely parallel to how you would do this. I mean, very simple thing, but it's important to be able to think economically about this. So a lot of times I see that students just talk about masses and this, and you got to kind of internalize the new terminology. You can't be an electrical engineer and call an inductor a mass, okay? Nobody is going to know what you're talking about, all right? So that's the trick here. So you really, you're really internalize this. Now, this you know is the damping rate, but this is a factor. If you solve this differential equation, you know what you're going to get. You're going to get an exponential, right? So your price at any moment t is going to be the price at some starting moment times this factor, right? This is the solution of this differential equation, all right? And this factor doesn't really have, we can call it the decay factor, right? So this is how fast the momentum decays, or if this is a position, how fast the position decays, all right? And it's called the discount factor in economics, all right? So this is a factor. A factor means you multiply it by something. It has no units. The discount rate, or the damping rate, has units 1/time, and that's precisely this gamma that's in here. Currently, I always use R instead of gamma for this, but this was still in the old days. This is a choice that's usually used in engineering, you know, that we use a gamma for that. All right. Okay. So that's a discount factor. Obviously, it depends on time. Why do I say obviously? Well, here's the definition, right? So it tells you, so the way you read these things as an engineer, and you all know that, this is just a function of I would take the TU blue here. These ones implicitly are a function of time, right? Here as engineers, we put the time be 0, and this function is, and then it goes to an equilibrium level. Now, what you see immediately is that, what does equilibrium mean? Now, equilibrium happens when the quantity demanded of this demander is the same as the quantity demanded by this market here. mechanically, when does equilibrium happen? If the velocity of the mass is equal to the velocity of the wall. All right, okay. And why is that the case? It is the case that because if there's no velocity difference, there's no way to extract kinetic energy, right? You need a velocity difference to make a collision or to do something, to drive a motor, okay? So as soon as velocities are to momentum what forces to displacement, okay? When forces are equal, then you cannot get a, and when velocities are equal, you can't get work out of the thing by changing the momentum, all right? And here that means that if the quantity demanded and supplied are equal, right, are they equal, that means there are no more price adjustments. It does not mean that the prices are the same. The price of this guy is humongous, all right? Now this is the price is much lower. Of course, the price per person here, per capita price, that may be the same if this thing consists of masses comparable to that, right? Okay. So the economic idea of equality of prices is not the right one. The correct one from this perspective is when demand equals supply, not the price are equal. You can get that by taking a reference frame and realizing that if you put this velocity as 0, then ultimately when the velocity is 0, because P is m times V, momentum will also be 0, and therefore the price will be 0. But that is because you use this as a reference frame. All right? Okay? So don't worry about all this complicated economic stuff. Just get the quantity demanded equal, and then you're okay. And use an inertial reference frame to do this, okay? The other thing you see is that there's a tradition in neoclassical economics that the markets adjust instantaneously to the equilibrium price, okay? So they assume that the market will do this, point, all right? Now that's not happening. That would happen if the discount rates were very, very large, right? Okay, so very, very small elasticity or very large thing, okay? So the transaction costs are humongous and the thing immediately stops after half a transaction, okay? Now, if prices do not adjust, why do classical economists say that prices should adjust instantaneously? Well, they say that because they reason that if they don't, you could make money. There's arbitrage because you know the price has got to be this, right? So you can make money if this person has a price that's too high. You just buy from him and sell to the others, right? So why is that still happening then? Okay. Well, it's happening because if you want to do this transaction, you're going to meet the same transaction cost. So you won't be able to make the total arbitrage, right? So these arguments of immediate reaction, they only work, okay, if these things are adjusted appropriately, all right? So if you just make a straight coupling, cotonk, right? Then then you will see boink, all right? And we'll do that. But otherwise, it just won't, because it's got to balance the transaction cost. The readjustment, the desire here has to be balanced, and the speed at which the price gets adjusted has to take account of the transaction costs. Okay, that's the big thing. So this is, in fact, the optimal thing to do. Okay, so if you try to cheat this system, you won't. You will just lose money. And anybody who thinks they can trade on the stock market thinking, hey, there's a price difference, usually it's because of transaction costs. There's always a reason. Now, in economics, there was a whole discussion about this. And I think, of course, I'm not an economist, and I'm certainly not one specialized in the history of it, but it's fair to say probably that there was a kind of firm belief, especially in the first part of the last century, the 19th century, 20th century, I mean, that markets would just always do the right thing and adjust themselves, all right, instantaneously. And then after the Wall Street crash of the 20s, this didn't happen, especially not in the labor market. So somehow the labor market did not adjust, and we still had just huge unemployment with people looking for jobs, all right? And there was economists like Keynes started to focus on what went wrong here, all right? And they developed various concepts to deal with it that they call, one of the Keynes' things was price rigidity, namely that prices do not adjust instantaneously. All right, and he has various models for it. And he wrote a really big book, and I've tried to read it. It says a title, I forgot the title. It's about interest rates and this and that, right? And one of the things about that book is it's very thick and it doesn't contain a single formula, right? And I don't know, as an engineer, it's always hard for me to read books without formulas because the ideas are so difficult it's very difficult to pin down what he's actually saying. Okay, so he says a lot of stuff, and you can get a lot of stuff out of it, and a lot of these concepts like price rigidity and the propensities, but everything is kind of qualitative. But the ideas, I think, are good. And I'd like to stress also how this dynamic view in economics that we have here in economic engineering gives a quantitative basis to his thinking. All right. Huh? Okay. So these are simple, a simple first order system. And those economists, that's basically what they deal with. I haven't seen second order systems in. I'd love to be corrected, but they just always have first order systems. Huh? Have you seen any second order systems, Berend? Huh?
No.
What about you, Jeroen? Huh? Now, lots of first order systems, right? Lots of exponentials. But second order systems, you have complex exponentials. I don't think they even know, well, they know what a complex number is, but they never use them, right? They don't use trigonometry. Huh? So the ease with which we can move from a first order system, which is relatively trivial, to a second order system in economic engineering is one of the powers. Let's just quickly recap what happened here, and then what I want to do with this this presentation is show you how you can model a simple futures trader with this, who has got an inventory and who has this cost of carry and everything, and how we can improve on the models that are there. All right, but first let's look at this broker dealer. So we had this system, right? Huh? This is like a broker and a demander. So this is the intermediary. What we add here is an inventory. So this trader now also has an inventory of stuff. The other one didn't. He's just buy and sell. He doesn't keep his own inventory. All right? He has no supply at hand that he can draw from. Now, in securities trading, a broker, this is typically called a broker, it's an intermediary. So he doesn't hold inventories and he doesn't demand. This was usually the client or something. And then this, when you are a broker dealer, that means that you also can hold the inventory, right? So if you're on the New York Stock Exchange, the specialist, he holds the inventory. A market maker on NASDAQ, they may or they may not, they may just, huh? Your real estate broker does not hold inventory, for instance. Huh? If you buy a house through a broker, he's just gonna go right to it, right? It's not that he has a bunch of houses in his lot, like a car dealership or something. All right. So this is what we sometimes known as a broker dealer. So I add this element. All right. Now, again, I give it some exogenous desire. All right, and see what this person do. And instead of looking at the price, I could have done that. I'm going to look at the inventory that he keeps. All right. So this is just a car dealership or maybe a currency trader, and here's a pile of currency or a stock trader, or a pile of these stocks just lying there, okay? He's making his transaction cost, and he has his demand and supply, all right? Now, I don't need to tell you guys what the differential equation is for this stock, right? Here it is, right? Huh? If you've paid any type of attention, you can dream these kind of equations, all right? And so I wrote it in standard form. Yeah, normally you would have a mass here, and then you would do it out, but I divided by it. So you'll see here the natural frequency, right? This thing is k divided by m, just the square of the natural frequency. Now this is this zeta, right, that you can define, I think, as b divided by m times 2 or something. Something like that. Huh? Is that right? I don't know. You can go sort that out. All right. So we leave the damping rate, which is the discount rate, as is. All right, because we have a B lying around. You don't do your put your microphone on mute. Huh? But now we have a couple of other things we can define. So this is this natural frequency, right? So economically, what would that correspond to? Well, what's happening, if you're a dealer, your stock, you sell, then your stock goes down, and then when it's too low, you start buying, so the stock goes up again, and then you start selling, and your stock goes down, and this is what happens, right? This is what you see. Okay, huh? So this would be what I would say is a trade cycle frequency, okay? And what's interesting is just by the setup, you see what this frequency's got to be. It's got to be k divided by m, square root. Okay, that's already quite different than most economics. They see lots of frequency. I think in the economy, they have 6 or 8 frequency called the relative inventory cycle list. One of the things you can do is look at a system and you just read off what this fraction of k over m is. Okay? Huh? Then you can define this damping rate. I don't know why I was trying to do it there, because here it just is, right? Yeah? I think I was right, because this is b divided by m, and then oh my god, oh no, there's a square root. So it's kind of complicated. So whatever. Now this is what we call a damping ratio. So it's a dimensionless number, right? So this is a frequency, this is sort of a rate. So this becomes a dimensionless number, you divide by 2. The reason you divide by 2, because you have two state variables, price and quality, right? We'll see that later. That's why that 2 is sitting here. Huh? Okay. And what we'll do, we'll borrow another word from Keynes, and he had something he called the propensity to consume. And it was the tendency, and propensity and tendency are the same word, to consume. Now, discounting is the same as consumption, right? So you just think of this broker as consuming this. I mean, maybe he's spending the money and doing nothing. He's just getting hot, all right? It's really good. So, but instead of the propensity to consume, I'll just call it a discount propensity, because we're looking at a trader here and not really consuming yet. I mean, that's probably what happens, okay? Huh? So it's not that Keynes defined it like this, it's just that I like to, use these words and give them a specific meaning, all right? So here you see, this is all you need to know about a second order system, right? Basically this, and then you're done, right? These two. So we have a frequency, and we have this damping ratio, all right? This propensity to consume. And that will tell us how the response will go. So we're going to look at 2 cases, the free response. We'll just have some stock here, let it go. And you'll see that this one goes exactly the same as a first order system, but you can imagine that this discount factor is going to be quite different. All right? In the first order system, this was an exponential, and this is not going to be an exponential. It's going to be an exponential, by the way. It's just not going to be a regular real exponential. There'll be an imaginary component in it, okay? Huh? In fact, we'll see a little later, you see, there is a theorem in mathematics that says every linear system has a sort of exponential solution. And so if you use these A matrix, you know, the A, B, C, D formulation, the solution looks like this. You do e to the power of some matrix, right? So this is a matrix. So this is an exponential, but it's super complicated. The whole matrix. How do you take e to the power of a matrix? Well, yeah, you can do it. All right. I'm not going to go into it, but you can see that the exponential function, they sometimes call this the exponential map if you do Lie group theory, is this like a really flexible thing that you can plug in almost anything here. So you can plug in e to the I, you can put an I here, and you can put some other stuff, j's, and you put all kinds of crap in there. All right? This is a really nice function. So one way of looking at it is if you just look at real exponentials, you're missing a lot, okay? So every linear system, no matter how complicated, will have some kind of solution that looks like an exponential, all right? That may be very difficult. So e to the I omega t is an exponential, but it does this. It doesn't look at all like this, all right? So, but it's still an exponential function, okay? So this is something that you get when you do linear systems theory, and that you miss if you try to fit real exponentials, right? So this discount factor becomes an exponential function, but of an arbitrary Lie group, as we would say. All right? And you can do this step response too. So here you take Q infinity, right? So what is the stock level at the now when the whole thing damps out? You quickly find out that it's the desire divided by the storage constant. Okay? Yeah, you know that's because f is k times q, isn't it? Sure, you want to go to infinity. So you know this is constant. So all right, and everything else is damped out. Okay? And then you go 1 time minus the discount factor. So everything is built into this discount factor here. Okay? So let's have a look at that discount. Here it is. So this discount factor is going to depend very much on your propensity to discount. Okay, so there are 3 cases, actually 2 cases. The propensity to discount is either smaller than 1 or it's larger than 1. And then there is a sort of in-between case, all right, where it's both. Both smaller or equal, bigger and equal. You know this. And we call that underdamped, critically damped, and overdamped, right? So you immediately recognize this if you go to this. Oh, I have the graph over here, right? So this is this is completely underdamped, right? So there's no damping at all. And this is what is critically damped. This is the green one. It looks almost like an exponential, except for this little part here, right? The beginning. Okay. And then if you crank up the damping even more, then you get this kind of stuff. It's below 1 and it goes really slow. All right. This is very familiar, isn't it? So when you use critical damping is when you have a door closer like this. You don't want it to slam, right? If you have saloon doors, you'll let it slam. And then when do you use an overdamp system? Does anybody know? When would you use that? In engineering? No? Critically damped, you know, right? So that gives you the fastest response with no overshoot, right? So underdamped you use when you want to have a really fast response, but you're willing to take a little bit of overshoot, like this one, right? So you go much quicker to your new stock level, right? Okay. All right. Because if you use critically damped, you won't overshoot, but it's going to take you much longer. This guy is already pretty much at his desired stock level. All right? Huh? I see you drawing something. What are you thinking of? Huh?
I'm thinking in the underdamp because it's still, but it goes, I don't know.
It's critically damped.
Yeah.
So if it's underdamped, it will overshoot a little bit. All right? Huh? The moment it doesn't overshoot, but doesn't undershoot either, right? Huh? That's critically damped. That's the best it can do by not overshooting. So if you don't want to allow any overshoot, you're going to pay a price, because you see, this thing settles, if you have some kind of settling time where it's within so much percent of your, so this is your stock level, that's your desired stock level, right? And you want to get there as fast as you can. It's better to overshoot a little bit and then come back, right? All right? That's just a much faster way to get there, right? Now, sometimes that's not desired with a door, but suppose you break a car at a traffic light. You could go much faster than a traffic light if you were able to overshoot a little bit, right? And then you're going to cause an accident. So you don't want to do that, all right? Okay? So then you would use a critically damped system. So if you had an inventory and you want to fill it to a certain level, but you can overshoot a bit, right? So there's some extra space there. I would use something like this, okay? Now, if you're just a dealer and you want to avoid any, and you don't pay much for using a lot, you can just go and, you know, like a currency dealer, they just have this drawer where they put some currency, some bills in. It doesn't cost them that much. And maybe they have to pay for being at the airport or something, right? So you'll be doing this, right? But if you want to fill your gas tank in your car, you won't be doing this because it will all come gushing out, right? But Shell has also got these tanks and they have a little overshoot thing, so they could do this, right? You see? Now, when would you do this? That's an interesting thing, huh? So you see, this thing, it's slower to converge to the equilibrium value, but initially it kind of takes off, right? So it kind of takes off. It is faster initially, and then in the long term it's slower. So if you think of an engineering application where you want to be faster initially and then slower later, you guys know anything?
Braking?
Yeah. So when you go to a traffic light, you first want to kind of, slam on your, push pretty hard, because you don't want to arrive at that traffic light, and then you want to arrive, and then here, and then you just kind of go boom, again, all right? Yeah, braking. That's typically what you do, So you get yourself, the worst, you get the worst over with, so you have to give yourself time to react, okay? With extra controls action. That's a good example. Another example is in suspension systems in cars. Okay, so what they do is when you have a suspension, you have the suspension is supposed to do. Well, suspension is actually this, So a suspension is this combination. So this is your car, and these are your shock dampers. I know shock damper's got this damping in there, and it's got this spring over it, right? If you see these things. Now, how do they tune those? They actually tune them to be in the overdamped, especially in sporty fuel cars, because what happens is you feel the little bumps in the road, right? Because it reacts quite big to a little irregularity in the road, so you kind of have a good feeling for the road and the pebbles and stuff. If it's too underdamped, you get this feeling of swinging, that you got in these old American cars. They have this thing where you kind of go seasick, this car going like this. So you want to have a little stiffer, a little more damp. So you do feel the little things, but the big bumps, you want to kind of dampen out really smoothly, right? I know there's no point adjusting to a huge pothole, you see? So if you think of an inventory system, you may have a system where you're a factory and you have some just-in-time delivery thing, and this is really important for you. You want direct reaction on the short term because you're going to shut down your factory if you don't have their goods available. I don't care about the long term so much. Okay. Okay. So what I'm doing here is I'm kind of saying you can think of these car analogies in terms of an inventory management system. So how you would do the braking, or how you would do the doorstop, of how you would do a suspension from an engineering perspective. That kind of analysis you can apply to an inventory system. All right. You could also use a price adjustment system and design that. Now there's a whole area called transient analysis, right? And it will give you all these parameters and maximum overshoot and this. And then if you design these PID controllers, you can set the parameters of a PID controller. Okay. So I've given names to these three different regimes, all right? And they're based on some economics that is well known. So economists tend to take the attitude that the only rational, or they call it also consistent, that's what I said, way to discount is exponentially. And the argument is based as follows. They say that the exponential function is the only function that is invariant under shifts in time, right? So if you look at the exponential function, you can move it over. You can start here, and except for the fact that it's a little lower, all the derivatives are going to look the same. Okay, you see that? So you can shift the exponential function, and then the derivatives. That's not true for say a quadratic function, right? So you'll be shifting, and they won't be the same. All right. Good. Okay. So the idea is that if you discount something a week later than now, that should be the same amount as if you do a year and a week later. You see, percentage-wise. Otherwise, it's kind of silly. Somebody could take advantage of you, because here your discounting behavior is different than it will be later. So you could just borrow some money and make this deal, and then when time comes around, I'm just going to make money, right? Now it so turns out that that was the argument that why you should always do that. Now, recently economists have been making counter arguments to that. So one counter argument is that, well, first it was noticed that people don't do that. That most people are hyperbolic discounters. That's what it's called. Okay, so they tend to discount things happening in the nearby future much faster than in the far future. Okay. So you make a much bigger distinction by receiving something today or up over a week from now compared to a year and a week from now. Okay? All right? So it's, or 10 years and 10 years in a week, or 50 years and 50 years in a week is to us the same. All right? This is not consistent with this, obviously, right? Huh? So it appears that human beings are different. At first, this was seen as an inconsistency, and now people are taking a slightly different. There are some researchers who take a different attitude. All right. So the argument is an interesting one, and I think it's correct. It says that this comes from our early, history as hunter-gatherers, right? So Suppose you need to feed yourself and you don't have this grocery store at now that you can walk to and just buy the stuff. So at a certain point you would make a kill or something. You would kill some animal. Now what are you going to do? Are you going to like consume this immediately, or and overeat, or are you going to wait and then consume a little bit later? All right. Now what people tend to do is, when they make a win, they tend to have a party and eat. And there's a good reason for this, because everything you have in your stomach, they can't really take away from you. So you start storing this stuff and other things. You have to make transaction cost and storage cost. Yeah, thanks. You go like, well, I don't even know, a year from now, this piece of meat will still be lying here, especially in the time of no refrigerators. It will just all be consumed by maggots, or I don't know what, right? Some other animal. So you have a tendency to discount the future very differently for your own survival. And this is what causes us to do the same thing on the stock market. And there's a feeling that that's irrational. But that's only based on the idea that you have some infinitely long living person with an infinite amount of money who can just discount everything, I believe. All right? And really, this tells you why this is the case. Because why do you get this overdamping? Well, the reason you get this overdamping is that your damping is just, is very high. That means your transaction costs are very, very large. So what you want to do is, and they're a percentage of the price, okay? So what you want to do is to minimize your transaction costs. You're gonna like bring all your transactions in the beginning, So then that percentage gets the smallest. All right, huh? That's what happens. Otherwise, your transaction costs just go up. And the transaction cost, for the way I'm reasoning, is going to be the storage cost. And it's actually what I want to come to in the next slide. But this is the idea. All right. So I want to look at it further in the next slide. And here you have something I would call a cyclical. Now, this is even more striking. Why would somebody with a car dealership be an exponential discounter? That will be ridiculous, because for this person, everything changes instantaneously. I mean, he wants to buy when inventories are low. He don't care about the time that's passed, and he knows the frequency at which this is happening. So he's going to all of a sudden prioritize buying and then selling and then buying and then selling. Okay, so he's going to switch all the time. See, this function here, it goes negative and positive, So this guy is going to switch all the time between buying and selling. So the total discount rate is going to be going between positive and negative, of course, because if he's overstocked, he's got to get rid of it, and he discounts it away. And if he's understocked, he's got to get it, all right? So this is certainly not going to be an exponential discounter, okay? The exponential discounter is really only good for somebody with money in a savings account that's sitting there indefinitely, all right? Yeah? And with no need for money or no storage cost, really, which a savings account is very little storage cost, okay? All right? Now, what I find mathematically kind of interesting, so you see that this old rate for a first order system, it looks like this, e to the minus gamma t, right? Now here you see that the new discount factors splits this. So it takes half of this, puts it over there, and the other half is spread out either over sinusoid or over this one and a linear function, or over a hyperbolic angle, all right? You see? So this explains also the factor half. Huh? All right. There's a lot to say about this kind of stuff, but I think what's important to see is that the formula contains an enormous amount of information about precisely how this trader is going to behave. It not only tells you what the modulation is, the envelope of this thing, right? How it is going to go down, which is this thing, right? But it also tells you the frequency, which you can find out, which depends on the damping ratio, the zeta factor, the propensity, all of it now. Now you try fitting this, okay, as an economist. It's impossible. You'll never figure it out. And then somebody changes this propensity, and then what? The thing looks completely different. In fact, they don't even consider this to be a linear model. This is called sinusoidal, and they think the sine function is the nonlinear function, which it is. But the difference is, what they will say is linear is the function itself, all right? And whereas for us, it's a differential equation, okay? This is a good thing to separate, okay? So we still can use the tools of linear analysis. In fact, you can rewrite this thing as an exponential, right? E to the I omega dt or something it is. Huh? It's a little bit complicated because you have another one, all right? Some mixture. You can even write this one as an exponential. It's e to the epsilon omega t, where epsilon is a number that if you square it, you get 0. This I, if you square it, you get -1, right? And this is epsilon is a number, if you square it, you get 0. It's called a dual number. Kind of interesting. And then you can see that this is sort of a cosine of an epsilon displacement, which is 1, right? And this is a sine, and the sine of a very small angle is proportional to the angle, right? You see that? So it's also kind of a cosine and a sine, decomposition of an exponential. Even this one is. It's just that instead of a circle, see a normal sine and a cosine, you have a circle. It's kind of interesting, right? And then here is a number I, and here is -1, and here is +1, right? So every 90 degrees is I. So I multiply by I, I get here, and 90 degrees, I do another 90 degrees, I multiply by I again, I get -1, right? But instead of a circle, you can use a hyperbola. So you go here, and then you go over there, so you go up, and then you do it another time, but instead of going backwards, you go forward. That's why here you will have I squared, and j squared is 1, all right? So it's a number that is not equal to 1, whose square is equal to 1, and then you can get a hyperbola. Anyway, those are the 3 possibilities, and they come out here. This is sometimes called hyperbolic geometry. This is linear geometry, you use that for shears and all, and this is circular elliptical geometry. It's a different type of geometry. Very pretty mathematics. This is not, this lecture really is not intended to show you all of that, although I find it very pretty. But what it is intended to show is that all of these are exponential solutions from linear equations. They're just very rich, okay? Much richer than you think. This is only a second-order system, okay? It's extremely rich. Look at the variety, all right? Look at the variety. So, in a certain sense, that's the power of this, right? Look how simple the system is. And then look at the response. And this captures a lot of stuff. There's a lot of discussion about what is hyperbolic. You should take a look at that. You know, hyperbolic discounting, all of this. Very long discussions. There it is. Just goes rolling out, okay? Now, the nice thing is you can use all these engineering tools that are developed for this. You can take the system, you can easily imagine how you build a controller, right? I mean, it's just controls 101. You take a second order system, build a PID controller, and see that you get the right transient response, okay? Trivial. So it's trivial to build an inventory control system like this. I don't think anybody has yet done it, no student has done it, but it is a nice thing to just do for Okay. And then you can build controllers for these things. So what I want to do with the rest of the lecture is go through a different example of a second order system. And this is a more evolved example than an inventory control system. And it corresponds to what is called the cost of carry model in the future markets. Okay. And here's the system that we're going to look at, right? So it's different than what we had before. Right now, the spring and the damper are in series, and the mass too, like that. Okay. And what makes that different? Now, what you'll see is that suppose this thing has this, and we're first going to talk mechanics, right? This has a velocity, whereas before we would have that the change of this would be equal to the velocity because the spring is attached to the mass. Now that's certainly not the case. Okay. So this velocity is equal to q dot plus the velocity of this this damper, right? Huh? And they have to add up in this way. It's quite different. Okay. But what is interesting here, in the previous example, right, the velocities were equal. They're sitting here, and the velocity of this is the velocity of that is the velocity of that guy, right? That's the way I welded them together. Okay. But the force of this and the force of that and the force of that, they're going to be different. They're going to add up, all right, if you make your free body diagram. Here, the situation is precisely reversed, okay? So instead of the forces adding up, now the velocities add up, okay? And the forces are all the same. So the force acting here is the same force acting here, and it's the same force acting there, okay? I mean, the force, you could just see the momentum flowing. It flows like this, right? And wherever it's pushing, it just goes back and it goes, okay? So it's sort of a dual type of situation. Now, what does that mean economically? For sometimes it's easier to this case, it's a little easier to do. You see, now we have to track the flow of the price, the flow of value, okay, rather than the flow of the goods. And that's always a little bit more abstract. So one thing you can do is make the electrical analog of the circuit, and then just start tracking the flow. Then the price becomes the flow variable. All right, so you can. So what is it? So I think what you do is you make a circuit. Here you have the coil, right? And then you have this guy, and then here is a resistor, right? So we earth it like that. Okay. So here you can kind of see what's happening. So if you took this thing away and you had a charge on this capacitor, okay, then what's going to happen? Or you make this really big, so you put a big wall there. Then this capacitor will just empty itself, over the resistor, right? I don't know. Do you guys draw a resistor like this, or do you do a resistor like this? Huh? That one, huh? I find it confusing with a spring, but and Americans they use I think this, and Europeans they use that. Oh, my confusing, right? Let's just do this then. You see? So what would be happening then? Then what's really happening is this store here just kind of discharges these apples or whatever is in there. It just gets bad or something, or it just goes away, right? They don't really go away. They get moved to the market, right? So this intermediary is now not somebody who is mitigating the trades, but rather is somebody who has you have to have custody over this storage, right? So he's the gatekeeper, and he has to make sure that's what custody means, so nothing happens. So if this B is infinitely big, then he's good, doing his job good. The other one is the other way around. All right. So this resistor is really big. This thing will keep its charge, right? So if you have a custodian with a very high B factor, so it really goes with 1 over B, right? So instead of writing F is VV, you write V is F divided by B, right? So that's what happens, right? So you turn the causality around. It's a bicausal element, right? So what's happening here is that if the goods are very desirable, but you have a really great custodian, you won't have much waste and loss. That's what this is. Okay? So the more desirable the goods are, so the higher this convenience force, the bigger the chances will get lost, right? Okay. So this custodian takes care of, a good custodian will keep your highly desirable goods, all right? And then I just add demand to this, okay? All right, so this is some storage. This is the custodian. This is the demander, right? Yes.
What actually is a custodian?
A custodian is somebody who takes care of your stuff. So if you go to some storage place and you say, can you please keep these goods in custody for me? He will say, okay, and he will charge you some fee, right? And this fee is exactly, what he's taking out, right? He's saying, all right, I'll keep your apples, but I'm going to eat 1 apple a day, right? And the amount of apples I take is going to be depending on the desirability of those apples, all right? That's what a custodian is. How do you say that in Dutch?
Bar?
Yeah, yeah. So it's a concept that you just use. So you can also call it a trust. So you trust somebody to. The trust is a little different. They can also trade on your behalf. A custodian only has to keep it on your behalf, right? So somebody you pay something to take care of your items. So you want to do, you want to get your. They have a storage place right here on the highway, right? I think next to the Race Planet, there's one of these custody places where you can put all your stuff in opslag, for instance. So it gets used a lot in these future markets, right? So let me explain it from that perspective. So you guys know what a future is or a forward? You know the difference between a future market and a spot market? Spot market means now, right? I buy oil now. That's spot price oil. And future oil is I buy oil March or 2025 oil. All right, so I do a contract to buy oil for delivery in March rather than right now, whatever it is. Right? No. 19th. Huh? My date was on US format. Okay, that's spot. And the other is future, right? So there are these future, the most markets, a lot of markets are spot markets. So if you go to the grocery store, that's a spot. You can't say to the grocery, hey, I'm going to buy half a spot for March delivery. I mean, that's just not the business they conduct. But others may, right? Now, and it was used for, it's very old, the future market, because it was used for by farmers a lot, right? So farmers, they know that they're going to have their harvest somewhere, I don't know, in the fall or the end of the summer, I don't know what, or the spring, I don't know when they have their harvest. But they'll need some money in advance to buy the seeds in order so they can get this harvest. So how are they going to raise the money? What they'll do, what they did in the old days, they would go to somebody who said, look, listen, I promise that I will sell this how many bushels of wheat to you for delivery and whatever the harvest of wheat is. If you give, and how much will you pay for that contract? You pay that much? You say, okay, this is the price. That's called the strike price. Okay, and he ponies up the money. And with that money, the farmer could buy the seeds. And then when he has his harvest, he's swimming in the tomatoes or whatever he's selling. And he says, here they are. And he keeps them for himself to sell whatever the spot price is there. Okay? Right, so that's how these were used. So it was a way to hedge. Okay, they used for hedging. So the farmer, he hedges his risk, and he can make investments. Okay, and also the farmer is not subjected now to price fluctuations. So suppose there's a bumper crop and everybody is selling this stuff, you're going to get a really bad price. Okay, all right, and if he borrows money, they go bankrupt. Whereas now he's guaranteed his price, he's got the money now, and he can go ahead. So it's a way of mitigating risk. The others, so we call that a hedger. All right, the farmer is the hedger. The person who takes the other hand of the contract and goes what we say long the futures contract. So he has a storage of these contracts. Okay, that's the speculator. Okay, so what's in it for him is that he thinks, well, when I'm going to buy this thing at a good discount, doesn't have to be cheap, at a discount to what I think I'm going to get. Okay, all right, when I actually sell it. So that will be my profit. Now I got enough money to buy this thing now, and this person really needs the money, so they both win. That's the idea. So you can think of trade as being, I got 100 apples, you want the pears, I give you that one, a pear. But here the trade is between, well, I have future oil, I do have cash now, and I'm doing this trade. It's perfectly legitimate, right? And the speculator just happens to be the person with the money, and we call him the speculator, but equally, this is just his side of the bargain. All right? Now, let me ask you this. What is the future price? How would you determine that? Okay? If you were a speculator. What would you give him? The farmer. How would you determine that? What thought process would you go through? Yeah.
The value of that amount of goods with some kind of discount.
Yeah, but what would be that discount factor? How would you determine your discount factor?
Is there a risk there is?
Yeah, that's one, right? Now let's forget about the risk a little bit. Would there still be a discount factor? Yeah. Yeah, you have the cost of storage, right? But does he really have a cost of storage? No. Because, so he's not worried about that. But what? Because he's got money. So the money also has its own cost of storage. What is that? That's called interest rate, right? So what happens to the speculator? He's not going to get interest, okay? So he's at the minimum, he's got to make the interest rate, okay? Now, interest rates are really low and there's no risk. That would mean prices are all the same, but they're not, and they vary from good to good, all right? Now, why would that be the case? And somebody said it across the storage. So suppose, and this is something that's called arbitrage. So suppose I have this future for delivery, okay, in March, and I want to hedge it out. That means I don't want to be exposed to any risk, okay? How would I do that? Going to the spot market. Well, what I would do is I have to deliver in March. But you know what I'll do? I'll buy it now, and I'll get myself storage, and I'll throw it in storage. And come March, I'll guarantee to be able to sell it for that price, right? So in this way, you'll be able to lock in a riskless profit. You understand that? Huh? So if there, so I have both things, and I locked out the risk, right? Well, the only risk I have is that the storage guy somehow stole it or that it went bad, right? Let's forget about that, right? All right. So you see that this risk component is not going to be very big because it's possible to arbitrage it away, to take an offsetting position, which I cover my risk. Okay. So what I need to know is my cost of storage, okay? And if I know that, I'll be able to do this, all right? And the cost of storage is also goes, that's this guy here, right? Huh? So this guy here, this is your storage. And this guy here tells you what the costs are associated with that storage. Okay? Now, this is the equation that I got out of, this is the Wikipedia, this is how they write it. So they will say the future price, so this is the price at some time t, is equal to the spot price, that's our P0, times this factor. Okay, so this is and I left out a minus sign. All right, there's a minus sign there. Okay, so you see, if I go back, you see this? So I can say F is S, so I can write the price at the moment t is equal to the price at the moment 0 times e to the minus gamma t, where gamma is this thing, right? Whatever it is.
There shouldn't be a minus, right? Because
Sorry, there should be. Yeah, because
it's minus higher.
you're right. That if I go from future to spot, right? You're thank you. Yes. Right. Okay. So what this is the Wikipedia article, right? You can look it up. What does this thing say? Well, it says it's like a first order system, right? Right? Why? It's all real numbers. Seriously. That's just exponential. It has to be, this has to be the solution to some first order system. Okay? Now, what do I have here? I have a second order system. So there's something weird going on here. I cannot get both this. The storage costs I can get in. That's this thing. Then there is some other friction. Let's forget about the interest rate. Okay? There's another type of friction that's got to do with the money flow. There are really two flows going on. That is one flow. Right? You have to go to beta to see the double flow model. So forget about this. So what people noticed is that this model wasn't working. Right? So they added something, and they added this C as something that counteracts it. And that C stands for convenience. And that is the C is what they call the convenience yield. Okay? And it's telling you there's another cost here, namely, that is the fact that when you have items of highly desirable in storage, that you're better off not leaving them in storage, but getting rid of them and selling them to somebody else. All right, and that is part of what they call the total economic loss. So that's the how do you call it? I forget the name, but you call them a separate word for it. They're not the task cost, but they that the price of something is not only what you pay for it, but also the cost of the opportunity foregone, the opportunity cost, right? Sort of an opportunity cost that has to be added in. Now, where does that come from in our model? Well, that comes from the spring force, of course, because the spring force that tells you how convenient this is for you. If the spring force is 0, that means you don't care. You don't want more, you don't want less. And the higher the spring force, the storage rate, the more convenient. We call that the convenience, right? So this is sort of this is the potential force, okay? We call it the scarcity, and the negative of that was the convenience force, okay? And this is what they would call a convenience yield. So they got something weird in here, that can turn this thing negative if these convenience yields are very high. So the convenience yield is 0, and you'll get this kind of thing, right? This kind of flow, and that's what they call contango. So you see that the future price is always higher than the spot price because it has to take account of the cost of carry, right? But sometimes they say the market is in backwardation. So this is a backwardation. So you'll see that the future price is lower than the cost price. Why? Because the items are highly in demand. All right? And that happens, and there's a couple of articles that describe really nicely But you can find these. Happens when inventories are really low. So when inventories are really low for something, people really want it, okay? And then the market goes in backwardation, meaning that there's so much desire for the goods now, you don't care about anything anymore. So the market turns around, okay? Now, if you look at this, you see these graphs, then all they can do is have to stay either be in contango or in backwardation. But if you look at how they describe the market, they'll say future trades, the market inverts. So it's not something static like that. So the moment it first can be in contango, and then after a while it goes into backwardation, and then they call it an inverted market, and then it goes in contango again, and then it goes in backwardation. All right, and it may shift a couple of times, usually not more than once. So it usually starts off in contango, otherwise the contract will never be made. And then because of inventory problems, it goes into backwardation, okay? And it starts doing this. So if you're thinking of a plot, it will go in contango, and then the market will invert, and it will go in backwardation, and then usually it will go in contango and kind of do this, if you look at these plots. Huh? All right? What really happens. But the theory can just do this or that. Now, if I show you this, what do you think of? Yeah. And damped, underdamped, critically damped? Yeah. That's the same, right? Yeah, so the market is in contango, then it goes into backwardation, and then it's, straight it out again. When you get close to strike price, the thing has to be, of course, if there's no more time left on the thing, it's what it is, okay? There's no more effects, okay? You see that? So, what is the problem from our perspective with this model? The problem is that you're just using a first order equation. What they need is this, if this is the discount factor, well, it's not the discount factor, it's a premium factor, so it's the inverse of the discount factor, right? Then they need this guy for a zeta like 0.9 or something, depending a little bit on the, You can perfectly predict when the market goes in backwardation, all right? And it's all due to these inventory effects that you add. You can't just add it in the exponent. You've got to add it here. This is where they're sitting, right? They're sitting in that imaginary part of the exponential, okay? You see that? And now we can imagine that this is what usually happens. So usually you see what must happen is these electricity costs must be high enough. They typically are pretty high. Otherwise, you wouldn't get these things going so few times. So usually they look at oil. Oil is shown as a lot of trading with this. Once we should have a student do a good job on this and show them how to do futures trading, the engineers, all right? So usually these markets are just regular contango, so there must be something like this, okay? Or the transaction cost is so high that they even go hyperbolic. But I think for some, so they look at oil all the time, because oil is expensive to store. How do you store oil, You know, they tried to do it, I think a few years ago during COVID, they gas in they hired these big old ships and they put them somewhere in the ocean and they fill them with oil, That's what these future traders do. So they hire all the storage in order to take advantage of these things, okay? And, but that's expensive, you can imagine, getting ships, and then the demand for ships is really high, for inventory is really high. So these custodians will start charging some enormous amount, now, all right? So these things quickly go away. Anyway, that's what they do. That's the game they play. They sit in London and they trade these, these futures in oil for Shell to keep these prices. That's their hedging strategy, and they just do it with fuel. It's interesting to read it. So yesterday evening I spent some more time reading through it. And
Certain quotes. I think I put one of the quotes here.
so before we do that, let's just do our analysis. So rather than at the start, you've got to look at the price, of course. We're looking at futures. So I turn this thing around a little bit. You get this differential equation. You know, so you get here minus, so I don't know. You know, sort that out, right? That's economic engineering. I mean, you just figure out what the differential equation is. Okay? And it basically looks the same as the one for the other second order system, the trailer, right? So except that the carry yield, so that is now, so that's that gamma that shows up. So that's the discount rate. So that will be the carry. That's what they call the usual cost of carry. If you add the convenience yield, they call it the full carry. All right. But this is just the regular carry yield. It's not B divided by M anymore, but K divided by B. All right. You see, the bigger B, the better job the custodial do, and the K is telling you, you know, what the storage does, right? Then this discount factor is now called, is actually, it should be, I think it should be -1 here, right? It's not the cost of carry. So, yeah, okay, so it just pushes it forward, this thing, all right? But it's not going to be a simple exponential. And zeta, I just call it the propensity to carry, right? The propensity to carry. So, what's your tendency is to want to carry the thing to exploration, you know, to arbitrage market, okay? And then you can, the other damn guys, they are the speculators, right? Because they are they're buying and selling and doing the backwardation, and these can be thought of as the hedgers. They just go in and they sit it out. All right. So this. Then I put here in the article, I have one sentence, and I spent some time on it to have. I have several. This is one paragraph, and I spent some time on that. The first sentence kind of describes the situation on the future markets from the perspective of a future trader. And this one kind of describes what happens from our perspective as an engineer, as a mechanical engineer, and tries to relate it to what happens in the future market. So let's just go through that. So a spring in compression generates the acceleration that forces the momentum to overshoot. Well, that's what happens here, right? So if the spring is compressed, this is going to push the thing up, right? Depending a little bit on how stiff this, or how much friction is here, okay? But what happens, so if you have an inventory, in compression, that means you're short. So if you are short inventory, so the inventories are low, right? Then you get, then the needs arise, exploration was a need, which bids up, forces are changes in price. So it's P dot, right? Which bids up the price to overshoot, and the overshoot is called a premium. Well, options trade called a premium over the settlement price. Okay, so the P infinity, that's the settlement price. So we go, this will be, and this is what they call the premium. And this is, so here it's trading at a discount, this is at a discount, and this is at a premium. All right. So this is a nice sentence. You can just, you can spend a little time with it to see how you can map your mechanical thinking, which you're all very good at, right? With this kind of future trading stuff, okay? And then if you take that perspective, you don't even have to calculate very much. You basically can write this down, and already by looking at this, you can already predict a lot of things about how the contaminant will go, what backwardation will go. And I think if you take a situation of oil or other type of commodities, a lot of things are known. These things are known, these things will be known, and you can get a long way, and then maybe these things change, and then all of a sudden the market will go in backwardation, and all of a sudden the response characteristics will change, Okay. So I think what I want to do is end this lecture here, and then we'll finish the whole thing off in the new year, all right? Because this is quite a lot of material, and it's important to stop here. And I think this example really shows for the first time a non-trivial application, okay? Where you can really see how looking at it from this point of view, you can really make a big impact, potentially, if you start applying it. So I know that you have a project in energy markets. I don't know if it's going to be relevant or not. Future markets, probably not in your case. But it's definitely interesting to have the interpretation lying around. You say, well, that's going to be the future price, okay? This is the stock price. All right? And you have something called the futures price. So if you're later in the future, then this is it. All right? So energy traders, they use the future markets a lot. Like, there's the Chicago, the CME or the CBOE, and there you can trade all these contracts. So they have futures in soybeans and a lot of these agricultural futures. But they also have financial futures, like interest rate futures and index futures and stock indices, and they're interesting instruments, and nobody has really modeled this yet within the group, and I think it's clear there's a lot of opportunities there, and what you want to do is if you want to model something like that, first of all, you start kind of analyzing the situation, but at some point you just got to do what Bailey is doing now and others, is you get out your laptop and get your slice thing and build yourself, and we'll be talking about all of that in the next semester after the new year, about how you can build electronic circuits and these endpoint systems where you can just say, okay, it's this market, this market. You start defining it, and then you can, you should be able to make a decent model of our future markets, okay, in a particular sector, okay. And then the other thing you can do is to go to, as a student, this is always possible because everyone wants to listen to you. Unfortunately, Shell has moved to London, but their future trading was always in London. But go to some company that may be interested in, can tell you what the problems are, etc. Okay. All right. So, any questions on this? Yes.
Is future trading only used in energy market?
No. You have agricultural futures, as I mentioned, right? So traditionally it was agricultural futures. So soybeans, pork bellies, all right? And that is the Chicago Mercantile Climate Exchange, and okay, does that. They're all traded in Chicago, the whole world. So if you're some Argentine selling beef or something, they list the grade and everything, and the exploration, and then the whole world trades in Chicago. All right. Then I just happen to know that Shell was, and oil companies have been very active trading. That's why I mentioned it. So if you go on the internet or look around, you'll see a lot of this stuff comes from oil, because it's so much more money than the other one. So they become quite sophisticated. But even more sophisticated is on financial futures, which I also mentioned, right? So you have interest rate futures. So these are futures that bet on interest rate. And you have index futures. You know what these are? An index, you know what an index is? A stock index? Yeah. So you buy a stock index in the future.
But do you then also have the cost of carry?
Yeah, because you can make dividends, right? Huh? For instance, huh? So maybe negative, those things are sometimes called negative carry, right? Because they actually pay you to keep them. Huh? In the old days, you had to get a safe in a big strong house and put in your contract so they would have negative carry. But nowadays, they would have positive carry, right? But now there will be negative carry. Huh? And the old brokers, they canceled it, but 20 years ago, a broker will still charge them, would you say, custody fees. There's a custody fees for holding your securities, right? So the old days, you held your own security. So you got a security, it was a piece of paper, you went home and you put it in your vault, right? And then you could give it to a broker to keep, right? And then, but that broker or that bank would charge you a small fee for keeping that, in their safe box, all right? But now with everything is electronic, these fees have gone away. But you still have brokers, I believe, a few years ago, I still saw brokers charging certain things custody fees, all right? And then the other thing is risk, so it's not the risk which you think, but counterparty risk. So if you trade with futures, the other guy, if he doesn't keep himself to the terms of the contract, he goes bankrupt or something, then, yeah, what are you going to do? Huh? You're sitting there with this dumb thing, all right? So then so there's a difference between futures and forwards. A forward is a future that is traded now just among individuals. So you and I make an agreement. That's called a forward. Futures are and then it can be anything at all. Futures are standardized, so you trade them through an exchange, okay? And the good thing about that is you have no idea who the counterparty is, and you don't care because the exchange guarantees that there's somebody taking up the thing, and that's not the exchange itself; it's the clearinghouse. So there's a clearinghouse, and they have a pile of money that if somebody goes bankrupt, the contract still gets settled. All right, huh? So. They also make you post margin, right? So they don't like you to go bankrupt. So if your future goes way out of the money, they're going to say, well, you got to post margin. So you got to put some money in there, right? It's like a bank when they charge you a mortgage. Yeah, sure, you get the money, but as soon as they start losing money, they're not. Huh? And if you don't pony up, they'll sell the future. Okay? But that gives you another cost, namely the clearinghouse costs, because if you trade those futures, you got to pay money to the clearinghouse so that they can guarantee that the trades will get settled, right? So the costs can be depends, depends on the instrument, how liquid it is, all right. But really, the sky is the limit, in future. So they just be adding on, as financial markets expand. Now, there's another theory of economics that's called the Arrow-Debreu approach to economics, and that's a theoretical part where futures play an important role. So for us, a good is an apple is an apple, okay, and it doesn't really matter if the apple exists now or tomorrow, it's still the same apple, okay? And it doesn't matter whether an apple is in Delft or if it's in New York, it's the same apple, all right? And what we do is the apple tomorrow will just be discounted according to this model, right? So if you do economic engineering, the apple tomorrow is just got this price and got that price, and you just predict it given what the system does, right? But that's not how the theory of general equilibrium and the Arrow-Debreu theory of general equilibrium works. Okay, so they don't have this kind of dynamics. So what they do is they consider apples tomorrow to be different apples than apples today. It sounds crazy, but this is what they do. All right, you get that? So and then for every time they need a separate market. You understand? Huh? So they can't carry them to different markets. So for them, the futures markets, they needed to determine their overall general equilibrium. So we had a general equilibrium, but it wasn't really general equilibrium in the arrow de root sense. It was just on a particular good. But what they will do is they want equilibrium in the spot and all possible future markets. Okay? And they also add geography. So they need a separate market for Delft as for Chicago and Shanghai. All right? We also don't do that. We'll just have to add some transportation costs, some damper, so if you have a resistor, then the current flows through, and that's how we would model it, right? And then it takes out the voltage drop is precisely the loss of desirability in terms of you transporting it from Holland to China. Okay? But they consider this all separate markets. So for them, future markets are essential in their concept of equilibrium. All right? Now, in my opinion, this is also and this makes these models hideously complicated because how many future markets are there? I mean, first of all, how many goods are there? And then if you need that good to be traded at all possible times in the future, I mean, what the heck, right? I mean, this is ridiculously complicated. And then you will have to prove mathematically there's some equilibrium and blah, blah, blah. And then they can do that because they call it market completion, all right? But one of the problems with the theory is that it's a theory, and as the old saying goes, only in theory are theory and practice the same. It's completely impractical, So you can't have that, and it's not so interesting because you're just observing everything. You're not predicting, you're not trading, and nobody does this way in practice. Okay, so. This is just to say that this is not just a little tiny example. It's also a way to say that the way general equilibrium would be done in economic engineering is precisely the way you did it a few lectures ago when you just had the big tensor or goods. And the way you would take care of time is through the laws of Newton, right? And that tells you, the tensor tells you how the different goods are related, so substitution effect, okay? That's the elasticity tensor. And the equations of motion tell you how the different future markets are related. Okay, right? And this is the way we model. So if you don't do that, the class of models is going to be huge. And by drawing up one of these guys, okay, you restrict that class very, very much. Basically to a class of models that only needs two parameters. There's omega n and there's zeta, right? There's two things you got to fit, right? And then you know everything. Now, I admit this is one good. If you have n good, you'll have to have n of these, and you have some cross terms, Then it will still kind of blow up anyway with 2n squared minus 1. I forget what it is, right? You have all these symmetric matrices, and so it will go with n squared. Take half, and I have to add 1 for the diagonal. But anyway, so you see, this is an enormous simplification, which makes it so easy to fit these. I mean, if you're an engineer, what would you do? How would you identify this model? Well, I mean, if you're an electrical engineer, you might put some generator and I'll look at the oscilloscope, what you get out, right? Now, what does that mean? That means you just identify where the poles are, right? I mean, I haven't done a Laplace analysis, but this thing is as a one conjugate pole pair. So all you need to know is what that pole is in the complex plane. Now, the one complex number is two numbers, so there you are, right? So you'll just, that's all you'll do, boom, right? And then you've got the model, and then you just look at the initial conditions, and then you find out, well, if I have this model, and this initial condition is going to do that, and when this external force is going to do that, then you're just running, okay? You don't have to fit 100 million future markets and all this stuff, okay? You see? It's a huge difference. Okay. So that is from a more theoretical perspective, the importance of future markets for economists. Okay. Now, even economists would agree, not all of them, but a lot of them, that this general equilibrium theory of de Broglie, which was highly touted, has failed to produce anything practical. Okay. There's a lot of theorems. And there's one theorem saying you can never find an equilibrium. It's the no-go theorem of Morgan, Sonnenschein, Mantel, De Bruyne. I always forget these things. Very complicated. So you're going to get lost in this, okay? So I don't want you to get lost in this, but what I want you to realize how the perspective changes and what the power of this is. Okay. Huh? Okay. But one thing is to say it's powerful, theoretically speaking, and the other is to do it, show it that you can actually solve a problem. And that's precisely why you guys are sitting at the table here. All right, that's your assignment for your master's degree, is to take this and show that you can actually do something like with it that somebody may need. All right, okay. So that step hasn't been done yet. All right. So that's a little lecture on this. There was something else I wanted to say, but it escaped me now. I went on this little, yeah, but I think it's important to see. Okay. Any further questions? I like these questions because they, huh? No. Huh? So you see, the only difficulty here is to somehow look at these economic situations and try to translate it in this kind of thing. But that's not very different than what the trouble is with the mechanical engineer. You get this project and they throw some thing at you, some mechanism, and you got to make a model, right? Huh? So you got to kind of, you got to do some work. You got to do some thinking. Like, what does it matter? I'm going to treat this as a unicycle, this car, or with 4 wheels. How am I going to model it? I only have a few elements. I'm starting off with a linear model. I just have a spring, I got a damper, and I got a mass, and then I got some active elements, transformers, and then we'll get to those, okay? But yet, you can build enormously complicated things, okay? You can make enormously complicated circuits, all right? Now, the trick here is to do exactly that and to organize it into this spice thing that we're building so that it really looks attractive. So I had a meeting with Beard, and it's really coming along, this model. And for me, this is one of the first models where we can really put a whole economy and a supply line, and it just works, okay? So in the new year, I'm confident. Well, at the Rabo meeting, we definitely will have a crackerjack demonstration. I was trying to bulldoze everybody over, right? Huh? So that's what you do too. You just look at a problem and you build something. First of all, start building it and then implement it. And then see what you get, right? Huh? Compare it to reality, right? Think about it, and then graduate with honors. All right. Okay. Well, then we can all sit this whole stand, and I'll see you guys in the new year, right?